Hello, it's Keith here, and this is lesson 5 of my 68,000 assembly programming tutorials. Now, over the last few weeks, we've been looking at various mathematical commands, and we've done addition, subtraction, division, multiplication, things like that. But because the 68,000 had so many commands, we've still only really scratched the surface of what it can do with mathematics. Now, this week, we're going to start to look at bit level commands. You probably know that on computers, numbers are represented by ones and zeros, and those ones and zeros are made up into hexadecimal, which make up our bytes and our words and our longs within our computer. There will be times within programming where we may need to do graphical things or other operations on parts of a number within a register, and we may want to work at the bit level to alter those numbers or to select certain bytes within a word, for example, and that's what we're going to be looking at today. Now, if you don't know what binary is, I'd suggest you do some research on that. I'm sure there's plenty of other videos you can look at, but you do need to have a basic understanding of what binary is before you look at today's lesson. So what are we going to do first? Well, first we're going to look at the AND, OR, EOR and NOT commands. These are logical operations, and in the case of AND, OR and EOR, they take two parameters, and the result will be a combination based on a logical rule of those two parameters. So let's take a look at those commands now. Now, AND is the most simple of them, and it is exactly what it sounds like. What AND will do is where both parameters are 1, the result will be 1 as well. But if both parameters aren't 1, the result will be 0. So if parameter 1 and parameter 2 are 1, the result will be 1, otherwise it will be 0. That's where the AND comes in. OR is also very logical. If you have a 1 in parameter 1 or parameter 2, the result will be 1, otherwise it will be 0. And finally, we have a command called EOR. Now, this is often known as XOR on the Z80 and some other systems, and what this does is it inverts the bits. So if the bit in parameter 2 is 1, then the bit in parameter 1 will be inverted. So you can see here we had a 1 here, but it is inverted to a 0 here. Now this 0 here is inverted by this 1 into this 1 here. But this 1 and this 0 are not inverted because there's a 0 here, so they're left the same. Now the final command we'll be looking at within this group is the NOT command. This is effectively an EOR of all the bits. It simply flips every bit within the parameter, and it doesn't take a second parameter in that case. Now when we're doing these commands, we don't do these commands on a single bit, we can actually do them on an entire byte or a word or a long. So what we can do is we can set one of our registers to a sequence of bits, we can then use a logical command with another parameter, and those bits specified within that parameter will be applied to our register's original value, and the result you can see here will apply using these same rules on all of the bits. And this gives us an excellent way of doing things like masking out some of the bits. We can use an AND command, for example, to just keep the top 4 bits within a byte. And of course, all the bits that are 0 within the mask will be lost in the result. Alternately, if we need to set some of the bits, we can use an OR command, and anything that was 1 within that parameter will be set to 1 in the result. The EOR command, of course, will flip a set of the bits as well. So you can see here that we can use AND and OR particularly for setting and clearing specific bits within a register if we need to get rid of them or we need to set them to 1. Okay, so let's have a go with this within our code. So what we're going to do in this example is basically what we just saw there. We're going to set D1 to D3 to this combination of bits here, which is just a testing pattern. We're going to show them to the screen. We're then going to use this same pattern with the AND, OR and EOR command, where we're going to set all the top nibble to 1s and all the bottom nibble to 0s. And then we're going to show the results on the screen. And we're also going to use the NOT command on register 3. Now we're doing these at the byte level for simplicity, but that's not the only thing you can do. You can do these at the word or the long level as well. So you can see here our test patterns, which are of course all the same at the start. And so the first command is using the AND command, and it's using the top nibble as 1 and the bottom nibble as 0 here. And you can see here that all the bits that were 1 have been retained, but all the bits that were 0 have been lost. So the AND command effectively only keeps the bits where the mask is 1. The OR command, on the other hand, you can see here, has actually set all of the top bits to 1. And that's what the OR command does. Where the bit is 1, the resulting register will be changed to 1. Where it isn't 1, it will be left unchanged. EOR, of course, will flip the bits where it's 1. You can see here, these bits have been flipped around, and they are now the opposite of these, but these bottom bits are unchanged. And the final one, the NOT command, flips all of the bits, and of course it doesn't take a second parameter. So there we go. So we can use AND, OR, EOR and NOT to change the bits within bytes, and as I say, that will be useful to us in a wide variety of cases that we're going to come across later. Now, we're not at a stage where we really want to display it yet, but in my past Z80 examples, I did show some visual representations of what the bits would do to the screen. So you can see here, when we do an EOR, or an XOR as it was called in Z80, we're effectively inverting black and white bits. When we do an AND, we're effectively only keeping the bits where we are using that one mask. And where we're doing an OR, we're effectively overlaying a second layer of bits to the screen. Now, we will see all of this in the 68000 series, in my platform specific series, when we start to look at graphics, but we're at a too early stage at this stage in the 68000. Now, as with a lot of commands on the 68000, the VASIMR assembler is doing a lot of helping to us. Of course, these commands don't just have to work with immediate values. We could equally do these with registers, so we could apply D1 to D0 like that. That's perfectly fine. But just for simplicity, we're using immediate values. However, as with a lot of other commands, VASIMR is automatically converting our simple AND command here to the true AND I command, which is the true 68000 command we have to use with an immediate value. Now, this is really a technicality. We don't need to worry about it. VASIMR does it all for us, and there's no negative effect of us using the AND command rather than the AND I command. But just to really tell you the details of the 68000, I do have to tell you that the AND I command is the true command for an immediate value, but just don't worry about it at this stage. Okay, so we've seen there we can change large numbers of bits within a register in one go. But what about if we actually want to test individual bits? Well, we can do this, but on the 68000 we can do more than just that. We can actually change the bit at the same time. Of course, we may need to test bits in a variety of cases. We might have a variable where some of the bits are used to represent a specific value. We may need to check the results that are returned from hardware, and certain bits within those results may have particular meanings. So there's going to be various times we need to test bits, but there's also going to be various times we may need to set, clear or flip bits within a register without changing the rest of that register. And of course, if we want to test the register at the same time, having a command that can do both at the same time is going to save us some work. Now, the 68000 has 4 commands that we can use. It's got the btest command, which will test a bit. That just checks a single bit, and what it does is it sets the 0 flag. The 0 flag will be set to 1 if the bit was 0, because 0 will then be true, and it will be set to 0 if the bit was 1. Now, it's kind of backwards maybe, but as I say, the 0 flag is considered to be, well, the 0 flag is true, 1, if the result was 0. So maybe it's a bit backwards, but that's the way it works. Now, as well as just testing a bit, we can actually change the bit as we test it. If we want to test the bit and then set it, we can use bset. If we want to clear the bit, we can use bclear. And if we want to change the bit, we can use bchange. So what do these do? Well, btst will test a bit but leave it unchanged. So the result after the test will be the same as before. But of course we will have that 0 flag set with the contents of the bit. If we want to test a bit and then set it, we can do that. And the result, whatever the original bit was, will be 1. Of course the 0 flag will represent the original bit's value. Then bclr will clear the bit. So whatever the bit was before, it will now be a 0. And of course the 0 flag will be set correctly. And bchange will change the bit. And this will be the equivalent of the EOR command. It will flip the bit that we tested, and we will have that result in the Z flag. Okay, so we've got a variety of commands there. Let's try them out. Okay, so we've defined this new command called show 0 here, and we're not going to look at the contents of it just yet. And what it will do is it will show the content of the 0 flag as a representation on screen, so we can see what that bit was when we did the test. What we're going to do is we're going to use this very simple test value of the bottommost 2 bits as 1, 0. We're going to apply each of the commands to that pair, and then we're going to show the results of the Z flag to screen, and we're going to show the results of the register each time. And the first time we're going to use the btest command, which won't change the register. Then we're going to use the set command. Then we're going to use the clear command, and then we're going to use the change command. And each time we'll see the results to the register and the results held in the 0 flag. So here's our starting register, and you can see we've read in the 2 bits here, and we're reading in bit 0 here first, and the 0 flag is telling us that that bit was 0. And then we read in the next bit here, just with this command here, and we can see the result was 1. So we've got the result we'd expect there. And of course, the register is unaffected by these commands. So now we move on to the second command here, and we're now using bset. So again, we get the 0 and the 1. So our test bset commands are reading in the bit values correctly. But when we show the register after these commands have been run, they're both set to 1. So we've changed the bits and we've set them to 1. Then we do the clear command, which again tests the bits we get the results shown to the screen here, but after we've processed it, the 2 bits have been changed to zeros, which is exactly what we'd expect from the description of the command. Finally, we use the bchange command, and we are, again, testing the 2 bits. We get a 0 and a 1 here, but when we show them to screen, we've then got a 1 and a 0, because these 2 bits have been flipped around. They've been inverted from the original value here. Now finally, I do want to point out that with all of these commands, we don't have to just use immediate values. We've used the immediate value here of #0 for bit 0 and the immediate value here of #1 for bit 1, but we can actually use another register and the value within those registers in exactly the same way, and it will work just fine. Now, one important thing to point out with these commands is that the bit numbers are represented from the right hand side. So bit 0 is here and this is bit 1 here, and so the last bit in an 8-bit number is actually bit 7 here. That's something a little bit confusing, but it's something you do have to get used to. Now, as I said, we can use a variety of registers and immediate parameters with these commands. It is quite important to understand with the 68000 that all of these times I'm showing you these commands, I'm only showing you a simple example of them, and to really understand the wide variety of commands you can and in some cases cannot use, I do have to ask you to look at other sources. And 2 I would recommend to you is, firstly, I have a cheat sheet on my website, and here it is, and you can see a very quick summary of the commands, and you can see whenever there's this EA, this means effective address, and this will usually support a wide variety of registers and addressing modes. But if you really want to get into the details of these commands and really know the full ins and outs, I would strongly suggest you use this document here. This is the official 68000 programming manual, and you can see here that we've got a wider variety of detail that I simply couldn't go into in these tutorials, and it will show a wide variety of examples, and you can even see the byte code that is produced, and there's some details here. But one thing you just do have to be careful of, this document in particular does cover the full range of the 68000 family, but in some cases you will see commands that aren't covered by the basic 68000 we're covering in our tutorials here. You'll see here that the 68010 is mentioned and onwards, but the 68000 isn't in this list. You see, this command simply doesn't exist in the processor we're using. So that's just something to be careful of if you're using this document, because while it's a superb document, it does cover all of the later processors, and that's not going to help us if we're programming a Genesis. So that's just something important I wanted to mention to you at this point. Now, we've looked at how to set bits and clear bits with ANDs and ORs and EORs. We've looked at how to do bit tests and clear individual bits. But what about if we want to actually move the bits around within the registers? This is something we're going to need to do quite a lot. On the 8 bits, it was essential for things like multiplication and division because those systems didn't have those commands. But even on the 68000, where we do have those commands, there'll be times where we may want to move the top nibble to the bottom nibble or something like that. Or we may want to move a few bits within the register around just to get the data into the correct format for a piece of hardware or something. So we're going to look at some of the commands that can allow us to do this today. Now, actually, there's so many commands, we're going to split them into 2 lessons. We're going to look at some of them next time, and we're going to look at the basic ones this time. So for today, we're just going to look at the simple commands that work within a single register and rotate the data around that single register. We're going to look at the ROL, ROR, LSL and LSR commands. Now, the L and the R in those at the end of those commands is left and right, and that is just the direction that they will move, and that will be exactly the same way as we see it on the screen. But the RO will stand for rotate, and the LS will stand for logical shift. Well, what do these mean? Well, rotate is very simple. The bits will move around within the register, and if they go off the top side of the register, they will come back on the bottom side. We'll see that in just a moment. Logical shift is more simple. When a bit is pushed off the top of a byte, it will just disappear. And the same if we're shifting to the right. If it moves off the bottom of the byte, it'll just disappear. So we're going to have a look at those. And it's going to be easiest if we see them in practical use. So what are we going to do? Well, as before, we're going to set one of our registers to a predefined sample value here, which is going to be 011010000. We're going to show that to screen as bits with this monitor bits command. And then we're going to do some rotations. First, we're going to rotate it left by 1 bit. And we're going to run the monitor. Then we're going to rotate it left by another bit, and we're going to show the monitor. Then we're going to move it right twice again, reversing the procedure, and we'll see the result. Then we're going to reset the register to the original value, and we're going to do the same with the logical shift commands, first shifting it to the left and then shifting it to the right. And in this way, we'll be able to see the difference between the rotate command and the logical shift command. Let's see what happens. Okay, so here's our starting value, and so we've done a rotate to the left by 1 bit. And you can see here that this bit has moved along, and this bit has moved along, and this bit has moved along. All the bits have moved along to the left. And this 0 here has actually been moved to here. And you can see that is true because when we do it again a second time, this bit moves here, this bit moves here, and this bit has moved to here. So with rotate left, when a bit goes off the left-hand side, it comes back onto the right-hand side of the same byte. And you can see that's definitely true because when we do our 2 rotates to the right, you can see that the effect is reversed. And this bit comes back to the right here, and then this 0 comes back to the right here. So after the 2 rotates to the right, the 2 rotates to the left have been entirely reversed, and the resulting value here is identical to the value here. Now what about logical shifts? Well, let's take a look. So here's our starting value, the same as it was here, and here's our first logical shift. And it may appear that it's exactly the same as when we use the rotate command here, but we will realise when we do the second one that it isn't. You see, on the second one, the one that was pushed off the left-hand side here was moved to the right-hand side here. But on the logical shift command, the bit that's been pushed off has disappeared. You see, whenever logical shift occurs, the new space that is created on the other side is filled with a 0. And you can see that when we reverse the procedure, because when we move this 1 to here, there's a 0 put in this place. Whereas before we had a 1 put in its place because that 1 was pushed off the other side here. And then when we shift again, another 0 is put in. So this is the difference between logical shift and rotate. If we rotate a byte 8 times, we will end up with the same byte as we started with because all of the bits will have been rotated around in a full 8 positions back to the starting position. If we do 8 logical shifts, we will end up with a byte that contains entirely zeros. That said, all of these commands, while we're doing them at the byte level here, can be done at other levels as well. It's not just the case that we can only do this at the byte level, it's just easiest to see it on the screen. So in addition to rotations and logical shifts, we have 2 other commands, rotate with extend and arithmetic shift. These are a little more complicated and we're going to look at them next time. So we've learned how to set bits and how to test bits, but what about if we actually want to use conditions and set the contents of registers based on a condition? Well, this is something that we would have to do multiple commands for on a Z80 or a 6502, but on the 68000 we have a quite curious command called SCC. Now, as with our other command BCC, the CC stands for condition code, and we can swap in a variety of commands in that position like non-zero or greater than equals or carry set or carry clear. So this will take on a variety of commands, and as I've said before, just check out my cheat sheet and you'll see that the variety of conditions you can use are shown here, and you should be able to use all of these with this SCC command. So we're going to try a variety of them now. Well, what does SCC do? Well, it's quite curious. What it does is it will set a register of our specification to true if the condition is true, or false if the condition is false. Of course, the condition is decided to be true or false based on the flags within the 68000, so this would usually follow a compare command or something like that, and that's what we're going to do today. Now, I said that the register will be set to true or false based on that condition. What does true and false mean? Well, in the case of the 68000, this command will define true to be 255, and it will consider false to be 0. So if the condition was true, our register will be set to 255. If our condition was false, it will be set to 0. This might be quite limiting to us, but of course if we needed to set a value of, for example, hexadecimal 80 if the condition was true, we could then follow it with an AND command and maybe filter it that way. But anyway, let's have a look at what this command can do for us. And one thing it can do is it can show very easily the status of the various condition codes to the screen for us. Let's try it out. So what are we going to do? Well, first of all, we're going to load some very simple test values into all of our registers here, just so we can see what these SCC commands can do. Then we're going to move a test value into D0, and then we're going to do a comparison, and we're going to then jump to this SCC test function. What this is then going to do is it's going to run SEQ, which is going to mean set if equals, and that's going to apply to D1. Then we're going to do SNE, set if not equals, to D2. Then we're going to do SCS, set carry set to D3, and FCC to set carry clear to D4. So effectively, D1 will be set if the 0 flag is set, D2 will be set if the 0 flag isn't set, D3 will be set if the carry flag is set, and D4 will be set if the carry flag is not set. And then we're going to show all of those registers to the screen, and we're going to return. Once we've done this first command comparing 10 to 10, we're going to compare 10 to 20, which is of course going to give a very different result. We're then going to run this test command again, and we're going to see the results a second time. So let's try it out. Well, what's happened? Well, the important thing to notice is the top 3 bytes of our longs have been unchanged because this command works at the byte level, and that's just something I wanted to make clear to you. But then when we've done our comparison between 10 and 10, well, of course 10 equals 10, so the register processed with SEQ has been set, and you can see that the bottom byte is now FF. But when we checked if it wasn't 0, well, of course that's not true, so the second byte has been set to 0. The third one, carry set, well, this would have been set if the first value was lower than the second one, which of course it isn't, so that again is 0. And then carry clear, well, that's the opposite of carry set, so of course that is indeed set to 255. And well, what about the second test? Well, in that case, we'd done the opposite. We'd set the value we were comparing to 20, which of course is higher, so all of these are now inverted. Well, 20 isn't equals to 10, so this one is now 0. But now the 0 flag is not 0, so this has been set to 255. Of course, now the second value is higher than the first value, so the carry flag is set. And finally, the carry is not clear, so this value has been set to 0. And there we go. So there we go. Quite a curious command, but as I say, it can only set the bottom byte of a register to 255. It's not one I've ever tended to use so far, but that's mainly because I tend to be used to the Z80 programming, which doesn't have any commands like that. So we've looked at a variety of commands with regards to bits there, and there's just two other commands I just wanted to include at this point, one of which is related to bits and another one that isn't, but it's very simple and quite important. So what are these? Well, these are the swap and the exchange command. What the swap command does is it swaps the top and bottom half of a register, because of course the registers are 32 bits and you can imagine them split into two 16-bit chunks, and swap will swap those two around. So effectively this could save us a lot of rotate commands, but it would of course be important with regards to the division commands, where the top word of the register will store the remainder and the bottom part will store the successful divisions. This could be very handy for you to get that remainder quickly into another register. As well as the swap command, we do have another command that's quite useful for moving things around, and that's the exchange command. What this does is it swaps the value of two registers without having to store the value in another intermediary register or the stack, so this is going to be much quicker. Let's try them out. So you can see here we've loaded a large number of 1s into D0 and a large number of 2s into D1. We show them to the screen and you can see the result of that here, and then we do this exchange command. And this has, as you can see, swapped over the two registers without any use of the stack or any other registers. So this is very convenient if we need to get specific values into specific registers before we call a function call. For example, my print char command always uses D0 as the character to print. Well, if the character I wanted to print was in D1, I can swap them over, run my command, and then maybe swap them back afterwards and get everything back to the way it was. Of course, the other command we're looking at is the swap command, which works within an individual register. So we've set this register to 1, 2, 3, 4, 5, 6, 7, 8, and you can see that here. We then run the swap command, and the top word and the bottom word have been swapped around. So you can see now it's 5, 6, 7, 8, 1, 2, 3, 4. Now the swap command only works at the word level within a long. You can't do swap 2 bytes within a word or anything, so if you wanted to do that you'd have to do some rotate commands or something like that. But these are two very interesting commands that the 68000 offers us, that offer quite a lot of power to us if we are trying to save performance and things, because it does allow us to quickly shift around two halves of a register or swap two registers over. So there we go. These are two commands you should bear in mind. So those are all the commands I wanted to discuss with you today. We're going to continue next time. We're going to look at some more rotating commands, and we're going to look at the extend bit, which has a great importance to some of the rotate commands and also to some of the mathematics when we want to work with very large numbers. Anyway, I hope you've enjoyed this week's lesson. Thanks for watching and goodbye.